So next functional component of AES is mixed column operation. Okay, so slightly we get into the operations of AES. So four basic operation, four fundamental operation in each and every round. So subite, inverse subite in reverse transformation, then shift row, inverse shift row, and mixed column and inverse mixed column operation. Finally, add round key. Add round key. Okay, so these are the functional components of each round of AES. Okay, each round of AES. Am I audible to you? Is this whiteboard visible to you?
Yes, ma'am.
Yes, ma'am.
Okay, good. So these are the functional components of AES round operation. So we have completed S-box, subbyte, and inverse subbyte operation. Okay. So next we're going to concentrate on mixed column, because shift row add round key is somewhat very simple operation as compared to subbyte and mixed column. Okay. So for mixed column alone, we need to know some fundamental concept called polynomial ring. Okay, so it will take 2 to 3 hours for completing a single operation. So that I'm going to concentrate on mixed column. Okay, and then we go ahead with the shift row and add row. Okay, so today we're going to discuss about the mixed column operation, and its reverse operation is known as inverse mixed column. Okay, inverse mixed column. Okay, so mixed column versus inverse mixed column. Okay, so the mixed column and inverse mixed column round is based on the number theory concept called polynomial ring. Okay, so we have a element called in algebraic theory we have a polynomial ring. Okay, what is that polynomial ring? Normally, gf of 2 power 2, gf of 2 is a prime polynomial. Sorry, prime field. Okay, so gf of 2 power 8 is a extension field. Okay, gf of 2 is a prime field. Gf of 2 power 8 is an extension field. Okay, in gf of 2, all the addition, subtraction, multiplication, everything over g modulo 2. Okay, gf of 2 or modulo 2. Here, all the elements, group elements are represented as polynomial. Okay, and modular reduction is by using m of x. Okay, and here the most important thing is the first element. The coefficient operations are based on 2, gf of 2. Okay, and polynomial addition, multiplication, the group operations are based on gf of 2 power 8 arithmetic. So we have to do modulo m of x. Okay, so I'll repeat again, because this is something important to understand polynomial ring. Gf of 2 power 8 is the extension field. Okay, so the gf of 2 power 8, the group elements are represented as polynomial. Okay, so now whenever you perform addition, subtraction with a group element, the coefficient addition, coefficient subtraction alone is based on the base gf of 2 arithmetic. Okay, and the entire group addition or group multiplication, for example, we have taken two polynomial, two group elements, each of with degree 7. Okay, x power 7 plus something something, and another polynomial is also x power 6 plus x power 4. When you multiply it, these two polynomial, definitely the resultant polynomial exceeds the degree. Okay, so to reduce or to make it as a finite element or to make it as a group element, we have to do modular reduction with m of x. Okay, so modular reduction with m of x. So coefficients operations are based on gf of 2, and entire polynomial addition, entire group addition, group operations are based on m of x. Okay, what is polynomial ring? In polynomial ring, the coefficient additions, coefficient arithmetic, coefficient addition, coefficient multiplication, everything is based on gf of 2 power x. Okay, so coefficient itself is polynomial. Okay, I'll repeat again. In polynomial ring, the coefficient itself is a polynomial. Okay, so the coefficient addition, coefficient reduction, everything is based on this gf of 2 power 8 arithmetic. Okay, and entire group element, group addition operation or multiplication operation to be reduced by m of x over polynomial ring. Okay, slightly a complex approach. This is a base behind this mixed column and inverse mixed column round. Okay, so I'm not going to start how to perform mixed column or inverse mixed column. We'll discuss that component on Monday. Okay, but to understand mixed column and inverse mixed column, you need a fundamental, you need understanding of the fundamental number theory concept, polynomial ring. So I'm going to concentrate on polynomial ring today. Monday we'll discuss about mixed column or inverse mixed column operation. Okay, so let's see. Assume we have two polynomial. Can you understand polynomial ring? Oh, okay, let's get into a new slide. So this is a funda for mixed column operation. Okay, so fundamental for mixed column operation that is known as polynomial ring. Okay. So in the polynomial ring, AS standard polynomial ring, AS document, AS is based on a polynomial ring with a degree 3. Okay, so it is also based on m of x power 4 plus 1. Okay, so this is not a AS standard irreducible polynomial. Okay, let's see. I will use a different notation because m of x is a AS standard irreducible polynomial. Let me take AS mixed column alone is based on a prime polynomial. Okay, x power 4 plus 1. Okay, and this AS mixed column round is based on a polynomial or group element with a degree 3. Okay, GF of 2 power 3. GF of 2 power 3. Okay, so GF of 2 power 3, here GF of 2 power 3 is a polynomial, but AS is based on polynomial ring over GF of 2 power 3. Okay, what is the meaning of this? That the element to be represented as polynomial with the coefficient x power 3 coefficient, x power 2 coefficient, x power 1 coefficient, x power 0 coefficient. Okay, the group element to be represented the polynomial like this. Okay, but actually, what are the coefficients? Coefficients are based on GF of 2 power 8 arithmetic. Okay, coefficients are based on again polynomial. Coefficients also be a polynomial, but in a normal suboid round, coefficients are GF of two elements, either 0 or 1. Okay, but here mixed column round, the coefficients are also polynomial. The coefficients are GF of 2 power 8 polynomial. Okay, so the coefficient addition, coefficient subtraction, everything is based on GF of 2 power 8 arithmetic. Okay, so let's represent the coefficient like this. A0 is, if A0 is a coefficient, A0 is nothing but a group element of GF of 2 power 8. Okay, it's a group element of GF of 2 power 8. Okay, so x power 1, A1, x power 2, A2, let it be, this is generalize it, let it be AI, A1, A2, A3, A4, everything is based on a coefficient of GF of 2 power 8. Okay, so now this is A3 into x power 3. Okay, let's start this. Okay, just carefully observe this polynomial. This is known as, this is based on indeterminate. Okay, so A0, A1, A2, A3, all these are polynomials over GF of 2 power 8. Okay, so this is known as polynomial ring. Okay, so this is a base for a mixed column round. AS document with the mixed column round is based on the polynomial with a degree 3, highest degree 3. Okay, so this is a polynomial ring. Okay, so the mixed column round is based on addition, subtraction over polynomial ring. Okay, so we need to know how to perform addition, subtraction, multiplication with this polynomial ring. Okay, so let's get into an example. Let's take two polynomial ring. Okay, A of x. Okay, A of x is a polynomial ring and B of x is a polynomial ring where coefficients are GF of 2 power 8 polynomial. Repeating again, A of x, B of x, polynomial ring with a degree 3. The coefficients of A of x and B of x are polynomial over GF of 2 power 8. Okay, so that's why it is, these two are a ring. Okay, now let's go for a multiplication. I need to multiply these two polynomial A of x to be multiplied by the B of x. Okay, where A of x, B of x both are polynomial ring. Okay, So I said again, I already said it. The coefficient reduction should be based on GF of 2 power 8. Okay, so let's do that one alone. How to perform the multiplication of two polynomial ring? Okay, so let's represent this A of x again. Okay, I have already represented, but again I'm going to represent this A of x as A of x and B of x. Okay, so A of x is a3 into x power 3 plus a2 into x power 2 plus a1 into x power 1 and a0 into x power 0. And this b of x is represented as b3 into x power 3 plus so b2 into x power 2 plus b1 into x power 1 plus b0 into x power 0. Okay, so we are going to multiply it. Okay, so coefficient is not gf of 2 arithmetic. Okay, so that you should not do modular reduction. Okay, so what we have to do here is x power 0. Okay, x power 0 coefficients are x power 0 coefficient a0 into b0. Okay, that will be a0 into b0 x power 0 coefficient. Okay, and this b0 to be multiplied with a1, so that you will get a1 into b0, and this is a2 into b0 and a3 into b0. So this actually coefficient of x power 3, and this is a coefficient of x power 2, and this is a coefficient of x power 1, and this is a coefficient of x power 0. Let's continue this. The b1 to be multiplied with a0. So this will be coefficient of, this is x and this is x power 0. Okay, so this will be x power 1 term. So the value will be a0 into b1, and the b1 to be multiplied with a1. So a1 into b1. Okay, I have not added x terms. Okay, indeterminate I have not added. Okay, so b1 into a2. So that is a2 into b1 and a3 into b1. So similarly, this x square term b2 to be multiplied with all these elements. So this is x power 0 term, x power 1 term, x power 2 term. Okay. So a0 into b0. Okay, actually this is a0 into b2 and a0 into b2 and a1 into b2, a2 into b2 and a3 into b2. Okay. So finally the x power 3 coefficient to be multiplied with this, so that this will be a0 into b3 and a1 into b3, a2 into b3 and a4 into b3. Okay, so just a multiplication. All these multiplications are gf of 2 power 8 operation. Okay, so this dot product, this dot operation, this dot operation is in gf of 2 power 8 operation, polynomial reduction. Okay, so this is actually a polynomial multiplication followed by polynomial reduction with AES standard irreducible polynomial. Okay, so that I have not solved, I have taken the coefficient as it is a0, b0, a1, b0, because all these ai, okay, ai and bi both are in gf of 2 power 8. Okay, so gf of 2 power 8, all these are polynomial. Okay, so let's represent all these things. Okay, this can be, this is actually a coefficient of okay, let's start with this. So this so this will be the coefficient of a0 into b0. Let it be, this is coefficient of x power 0 term, c0, and this is actually coefficient of x power 1 term. What is x power 1 term? a1 into b0 XOR with a0 into b. Okay, so this is a coefficient of x power 1 term, and a2 into b0 XOR with a1 into b1 XOR with a0 into b2. This is a coefficient of x power 2 term, and this is a coefficient of x power 3 term, and this is a coefficient of x power 4 term, and this will be x power 5, and this is x power 6 coefficient of x power 6. So I have represented by using the term c. Okay, so this is coefficient of x power 0, x power 1, x power 2, x power 3, x power 4, x power 5, x power 6. Okay, but remember one thing, these two polynomials are over GF of 2 power 3 ring. Okay, so the maximum degree should never exceed 3. Okay, it should never exceed 3. You have to do modular reduction with these three polynomials. Okay, so let's get into this because we are going to learn a shortcut for this because it's a time complex operation. Okay, so let's rewrite this. Okay, what is C0? C0 is nothing but A0 into B0. Okay, A0 into B0 over GF of 2 power 8 multiplication. Okay, and what is C1? C1 is A0 into B1 XOR with, actually this is a XOR operation, addition is XOR. Okay, A0 into B1. Okay, let's write like this. A1 into B0 plus A0 into B1. Okay, so the third coefficient is C3 is, sorry, C2 is these two polynomial, these three polynomial to be added. So A2, so this will be A2 into B0 XOR with A1 into B1 XOR with A0 into B2. Okay, so similarly, the C3, C4, C5, 6 is C3. C3 is these four polynomials. So let's write in the same order. So for better understanding, so A3 into B0 XOR with A2 into B1 XOR with A1 into B2 XOR with XOR with A0 into B3. Okay. Now C4 coefficient for x power 4 term, coefficient for x power 4 term. So these three elements. So A3 into B1 XOR with A2 into B2 XOR with A1 into B3. Okay. So C6 is nothing but, okay, sorry, C5. So C5, these two polynomial. So A3 into B2 XOR with A2 into B3. Okay, let's proceed with one more polynomial. Let us say 6. Okay, so coefficient of x power 6. Okay, so C6 is nothing but A4 into B3. Okay, now what we did, we have
A3.
which one? Huh? It is
C6.
A0, A1. Okay, good. Thank you. Okay, so this is A3 into B3. Okay, this is A3 dot B3. Now, till this, no problem. Okay, okay, till C3, the degree is less than 4. Okay, so because this is ring over GF of 2 power 3, ring over GF of 2 power 3, the maximum degree should never exceed 3. Okay, but what about these three coefficients, these three elements, we have to reduce it by using M of x. Okay, so for this polynomial ring, A is Rendall represented the x power 4 plus 1 as a M of x polynomial. Okay, prime polynomial, to reduce this J of the 4 element is by using x power 4 plus 1. Okay, but in x power 4 plus 1, a very simple thing is, because it's a polynomial with only two terms. Okay, to reduce this, okay, for example, because to generalize this, I'm going to have one example here. Let me take x power 5 mod x power 4 plus 1. Okay, so x power 5 mod x power 4 plus 1 is nothing but x power 5. Okay, you need to find out the remainder, x power 4 plus 1. So one time, so x power 4 into x is x power 5 plus x. Okay, so this is GF of 2 power 3. So that we have to do the subtraction, modulo 2 subtraction. So when you perform modulo 2 subtraction, these two will cancel out. So minus 1 x is nothing but x. Okay, so x power 5 mod x power 4 plus 1. Okay, I'll write it here. X power 5 mod x power 4 plus 1 is nothing but x. Okay, so let's go ahead with one more because we need a general notation for this. X power 6 mod x power 4 plus 1. Okay, so if it is so, okay, just divide it. X power 6, x power 4 plus 1. Now this will be x squared, coefficient x squared plus x power 4 is x power 6 plus x squared. Okay, these two will cancel out, you will get x squared. Okay, now what about this? This is x squared. Okay, so in this manner we can do this. So very simple generalized formula for this is x power I mod x power 4 plus 1 is nothing but, it's a general formula, so I can write it out in this notation, x power I. Okay, but this is true only with a monic polynomial. All these are monic polynomial. What do you mean by monic polynomial? A polynomial with only one term. Okay, monic polynomial. This formula is suitable only for monic polynomial. Okay, so x power I mod x power 4 plus 1, I can write it as x power I mod 4. I mod 4. Because after doing a modular reduction, you are again getting a monic polynomial. X power 5 mod x power 4 plus 1 is x. X power 6 mod x power 4 plus 1 is x square. We are getting a monic polynomial. Okay. So let's try this example here. X power I is nothing but 5. Okay. So I is 5. 5 mod 4 is 1. Okay, so we are getting x power 1. Let's get into this x power 6. I is 6. 6 mod 4 is 2. We are getting 2. Okay, so this is possible for monic polynomial reduction. Okay, clear? Can you understand? Can you understand this general notation? Can you understand this general notation? Students?
Yes, ma'am.
Yes, ma'am.
Okay. Now see, this is x power 0 term, no need to reduce it. Okay. So this is x power 1 term, no need to worry about this. So this is x power 2, no need for reduction. And this is x power 3 term, no need for reduction. But this is actually x power 4 coefficient, and this is x power 5 coefficient, and this is x power 6 coefficient. Okay. So reduction required for these three coefficients. Okay, so C4 x power 4, C5 x power 5, C6 x power 6. Okay, now here in this case, apply this equation. Okay, so C4 x power I mod x power 4 plus 1. Okay, so this is nothing but x power 4. Okay, that is x power I, this term x power 4 mod 4. 4 mod 4 is 0. So this can be rewritten as x power 4. Okay. Let me use the same red color. So this x power C4 coefficient, this indeterminate can be replaced as x power 4 mod I. Okay, this rule. Okay, if you apply this rule, this will be C4, the coefficient of x power 4 mod 4, 0. Okay, now this will be C5. C5 will be the coefficient of x power I mod 4. X power I mod 4 is 1. X power 1. Okay. Now these, let it be these two coefficient is different, so let it have a different notation. So this is C5 x power 1. Okay, C5 x power 1. Now this will be x power 6, x power 6 mod 4, because all these things are not for understanding of polynomial ring. Mixed column round is a very complex operation, but we have to do it in a faster manner. Okay, so what we are learning is a faster way of doing arithmetic on polynomial ring. That's it. Okay, so polynomial ring is not complex. It is very simple. Coefficient reduction is based on polynomial over GF of 2 power 8. Entire reduction is based on GF of 2 power 3. Nothing else. Okay, but every time whenever you perform reduction, it requires division. Okay, so division is a time complex operation. We have to remove the number of division, maximum number of division. So what we are learning is a shorter or a better way of doing polynomial ring arithmetic. Okay, So now C x power 6, x power 6, x power I mod 4, when you apply it, this will be x square. Okay, so this will be the term in determinant will be x square, and this coefficient will remain same. So this will be 6. Okay, so now the addition is XOR operation, you know. So this element, okay, so see x power 3 element, I have only one x power 3 element. Okay, so this is a x power 3 element. Okay, only one, because this is x squared, this is x power 1, and this is x power 0, this is x power 3. So only one element for x power 3. But take it out this x squared, we have two elements for x squared, two coefficient for x squared. So one is C2, another one is C6. Okay, now we have two coefficient for x power 1. One is C1, another one is C5. And now we have two coefficient for x power 0, that is C0 and C4. Okay, so let's write the final equation like this. Okay, so A of x into B of x. Okay, so this is nothing but D of x. Okay, how can I represent D of x? D of x based on only 4 term. Okay, so x power 4 term. Okay, so x power 4 term, x power 3 term, x square term, x power 1 term, and sorry, only 4 terms. So this will be x power 3, x power 2, x power 1, and x power 0. So this is x power 3 term, x power 2 coefficient, x power 1 coefficient, and x power 0 coefficient. Okay, so what is the coefficient of x power 0? C0, okay, XOR with C4, okay, x power 0 coefficient. So C0 and C4, okay, so C0 to be added with C4. So this will be C0 XOR with C4, okay. Now plus x power 1 term C1 XOR with C5, okay, so this will be C1 XOR with C5, okay, plus x square term C2 XOR with C6, okay, so this will be C2 XOR with C6, plus x power 3 term only one thing, which is C3, okay. So now actually I have written this based on this, okay. Now I'm going to elaborate this. Let me take this one alone, okay. So this is actually our required reduced polynomial, okay. So now we have to expand this coefficients alone, okay. So reduced polynomial is this, okay. GF of 2 power 3 polynomial, because none of the term, sorry, there is no term with x power 4 or x power something greater than 3, okay. So this is a reduced polynomial over GF of 2 power. Okay, now just elaborate it. What is C3? What is C3 actually? C3 is nothing but A3 into B3 XOR with A2 into B2 XOR with A1 into B1 XOR with A0 into B3. Okay, and C2 and C6. Okay, so C2 is A2 into B0, A1 into B1, A0 into B2. That one to be XOR with C6. C6 is A3 into B3. Okay, so every coefficient, in every coefficient we have 4 terms. Okay, so we can do it just by doing a simple matrix multiplication. Okay, so let's do this. Okay, have you taken this coefficient alone in your paper, in your notebook? Have you taken C1, C0, C1, C2, C3, C4, C5, C6? Have you taken? Can you dictate me?
Yes, ma'am.
Okay, good. So now go for this. Okay, so we need to perform multiplication A of x into B of x, polynomial ring multiplication. We need to compute D of x. Okay, so actually D of x is also over GF of 2 power 3. Okay, only 4 terms are available. Okay, so x power 0 term, x power 1 term, x power 2 term, and x power 3 term. So D0 is a coefficient of x power 0 term, and D1 coefficient of x power 1 term, D2 coefficient of x power 2 term, and D3 coefficient of x power 3 term. Okay, I'm going to represent in terms of matrix. Okay, so this polynomial is the coefficient of this polynomial is represented as a matrix like this. As you know already, this is actually a coefficient of the most significant bit or the coefficient of the higher degree element. Okay, so D3 is the coefficient of x power 3 term, D2 is the coefficient of x power 2 term, D1 is the coefficient of x power 1 term, D0 is the coefficient of x power 0 term. Okay, so this can be achieved by using a simple multiplication, because this is x power 0 term, C0 and C4. C0 and C4 is based on A and B value. Okay, so let me generalize it. Okay, A0, A3 and A2, A1. Okay, so the subsequent operations, subsequent elements are A1, A0, I have written this one based on coefficients Ci values. Okay, A1, A0, A3 and A2, and D2 is nothing but D2 is A2, A1, A0 and A3, and D3 is nothing but A3, A2, A1 and A0. Okay, so this is equal, this is multiplied with B0, B1, B2, B3. Okay, how I got this matrix? Okay, let's see. Let's see this. This is actually a D0. Okay, coefficient of x power 0 term. Okay. Okay, so this is actually D0, coefficient of x power 0 term. What is actually D0? D0 is nothing but C0 XOR with C4. What is C0? What is C0? What is C0? What is C0 coefficient?
A0, B0.
A0, B0.
A0 into B0. Okay, and C4?
A3,
What
B1.
is A3 into B1? Then
Sir, A2, B2.
A2 into B2? Then
Sir, A1, B3.
A1 into B3. Okay, actually you have to write this. After that only you have to derive this matrix. Okay, so similarly, let's go for one more element. Okay, D1 is a coefficient of x power 1 term. Okay, D1 is a coefficient of x power 1 term. X power 1 term is C1 XOR with the C5. C1 XOR with the C5. Okay, so C1 XOR with C5. What is C1? What is C1?
A1, B0.
A1 B0. Then
XOR A0, B1.
A0 into B1. Then
XOR A3 dot B2.
A3 dot B2. Okay, then
XOR A2 dot B3.
XOR with A2 dot B3. Okay, let's complete remaining two, because sometimes you may get confusion. D2 is C2 XOR with the C6. Okay, C2 XOR with the C6. Okay, C2 XOR with the C6. So D2 is coefficient of x power 2. Okay, C2 XOR with the C6. What is C2?
A2, B0.
Okay,
XOR A1, B1.
good. Then
XOR A0, B2.
Then
A3, B3.
okay. So finally, one more coefficient, D3. What is D3? D3 is the coefficient of x3. The coefficient of x3 is C3. Okay. So what is C3?
A3, B0.
So A3 into B0 XOR with
A2, B0, B1.
XOR with
A1, B2.
XOR with
A0, B3.
A naught and B3. Now, actually, you have to derive this first. Okay. So, this is actually a coefficient of x power 0 term. Okay. Coefficient of x power 0 term, x power 1 term, x power 2 term, and x power 3 term. Okay. So, now observe this here. All these elements are B0. Okay, all these elements are B0. Okay, now here all the elements are second elements are B1. All the second elements are B2. Here all the second elements are B3. So that this dot product can also be a matrix product, matrix multiplication. Okay, so now see, let's see here. And when you write this column, you should be careful. Okay, the first row to be filled with the first four elements. What is the first four element? A0, A1, A2, A3. Okay, so fill it out. A0, A1, A2, A3. And then the first row to be filled by the first element of this A0, then A3 and A2, A1. Okay, so A0, A3, A2, A1. Okay, first fill first row and first column. Then do the matrix multiplication, you will get the same result. Okay, A0 into B0, A3 into B1, A2 into B2, and A1 into B3. So this is the first element, that is B0. Similarly, A1 into A0, sorry, A1 into B0, okay, A1 into B0 plus A0 into B1 plus A3 into B2 plus A2 into B3. So this will be B1. Okay. So the final element can be computed just by doing a simple matrix multiplication. Okay, actually what we are doing is some multiplication over polynomial ring, but multiplication over polynomial ring can be simplified as simple matrix multiplication. Okay, one matrix, a 4 by 4 matrix to be multiplied with a row matrix. Okay, with a, sorry, a column matrix. Okay, so column vector, entire 4 by 4 matrix to be multiplied with a column vector. Okay, so what we can do is in mixed column round is based on a multiplication of two polynomial ring. Okay, but if you perform that operation by using direct approach, you need to do a modular reduction several times. It will be a time consuming operation. So to avoid that, what we are doing here is the mixed column round is represented as a product of a matrix with a column vector. Okay, so matrix to be represented and it should be multiplied with a column vector. So mixed column round is based on multiplication, polynomial ring multiplication, GF of 2 power 3 polynomial ring multiplication operation. But actually we can do that operation in a simplified manner by applying matrix product, sorry, matrix multiplication. Okay, so this is one understanding required for a mixed column round, and another understanding, another simplified version for GF of 2 power 8 multiplication. Okay, so this is a simplified version for GF of 2 power 3 polynomial ring multiplication. Okay, polynomial ring multiplication can be simplified like this. Okay, this is a simplification of polynomial ring multiplication. Okay, so you have to understand one more concept for mixed column, that is simplest way of doing multiplication over GF of 2 power 8. Okay, let's proceed with it. But before that, is it clear to you? Is this concept clear to you? Multiplication of the polynomial ring, is it clear? Okay, A of x into B of x. We need to find out D of x. Okay, so we can do it just by using a simple matrix multiplication. Clear? But I will convert this one into a PDF notes, then I will share it as a GCL. Okay, all this workout will be useful for you. Any doubt? Students, any doubt? I need to complete one more simplification over GF of 2 power 8 arithmetic for a mixed column in prerequisite. Okay, shall I proceed with that? Okay. So here the mixed column round, we need to do a matrix multiplication like this. Okay. What are those A0? What is actually AI? What is BI? What is AI and BI? What is AI and BI? What is AI? What is AI, pa? AI, what is AI?
Polynomial over GF of 2
So
power
this is
8.
over GF of 2 power 8 polynomial. Okay. So when you perform this, A0 to be multiplied with B0. So A0 into B0, this itself is a polynomial multiplication. Okay. Polynomial multiplication, if the degree exceeds 7, you have to do modular reduction with M of x. What is it, M of x? What is that M of x? What is it, M of x? After multiplication, polynomial multiplication, if the degree exceeds 7, you have to do modular reduction with M of x. What is that M of x?
A is standard M of x.
A is a standard irreducible polynomial x power 8 plus x power 4 plus x cube plus x plus 1. Okay, so this row, this first element alone, okay, to compute this first element alone, first coefficient alone, it requires a maximum of 4 multiplication and 4 division maximum. Okay, if the degree exceeds 7, you have to do reduction. 4 multiplication and 4 division. Okay, so it's a very time consuming operation, highly time consuming operation. You need some shortcut for this. Okay, so here what we are going to do here is we need a shortcut for multiplication over GF of 2 power 8 polynomial. Okay, multiplication over GF of 2 power 8 polynomial. Okay, in a binary number, multiplication by 2. Can you simplify multiplication by 2? I have a binary number. Let it be 1, 1, 1. Multiplication by 2. What is multiplication by 2? 1, 1, 1. Any simplification for multiplication by 2 for binary number? Let's take this. 0, 0, 1, 0. Okay, it's 2. Multiplication by 2. Okay, I have to multiply by 2. If you multiply by 2, what will be the result? If you multiply by 2, what will be the result? Binary multiplication. 0, 0, 1, 0 into 0, 0, 1, 0. What is the result?
0
2
1
into
0
2
0.
என்னடா 4 இல்லையா? So this will be 0,
Shift operation.
0, 1, 0, 0, you know. So this is the shift operation, single shifting. Okay, so multiplication by 2 in the binary concept is a shift. Okay, only one shift, not circular shift, single shift. Okay, so multiplication by 2 is a shift operation. So we have to think it like this. Okay, so we have to make this polynomial operation. Okay, because shift is not a time consuming operation. We can do it by using a register. Okay, but multiplication requires add or subtract. Okay, but shifting is simple operation. So we have to think like that. So this multiplication can be like this, shifting to us left. Okay, so that is the idea here. We're going to simplify this matrix polynomial multiplication in terms of shift operation. Okay, so instead of using multiplier and multiplication and subtractor and adder, we have to do it by using shift. Okay, that is the idea. Okay, let's see this. I will complete within 10 minutes, okay? Because it's time 11:45. I will complete within 10 minutes. Okay, so let's take a polynomial f of x, okay, over gf of 2 power 8. Okay, so it's over gf of 2 power 8, so there will be only 8 terms, x power 0 term, okay, then x power 1 term, x power 2, x power 3 term, x power 3 term, then x power 4 term, x power 5, x power 5, x power 6 term, and 7. Okay, so x power 6, x power 7. Okay, so now these polynomials are over gf of 2 power 8. Okay, so gf of 2 power 8. So the coefficients are either 0 or 1. Okay, the coefficient can be either 0 or 1. Okay, but it may be either 0 or 1. Okay, so there are two options, so that I am going to use a variable here, b0, and the coefficient of x power 1 is b1, b2, The coefficient of x power 3 is b3, coefficient of x power 4 is b4, and coefficient of x power 5 is b5, and coefficient of x power 6 is b6, and this will be b7. Okay, where bi is either 0 or 1, because this is over gf of 2 power 8 simplification, multiplication simplification, sorry, simplification for multiplication. Okay, so gf of 2 power 8 group element. Okay, so let's represent that polynomial or group element like this, f of x. Okay, so if the particular term is 0, and then the entire, if the particular coefficient is 0, the entire term will be 0. Okay, so let's take a modic polynomial, okay, which exceeds the degree 7, x power 8. Okay, but x power 8 is not a group element over gf of 2 power 8. It's not a group element. Then what we have to do to make it as a group element, we have to do modular action with m of x. Okay, so what is it m of x? A is standard m of x. A is standard m of x is x power 8 plus x power 4 plus x power 3 plus x plus 1. Okay, please verify it. X power 8, x power 4. Okay. So A is standard irreducible polynomial. So we have to divide it. Okay. So when you divide it, what is the result? X power 8 plus x power 4 plus x power 3 plus x plus 1 to be divided by x power 8. Okay. So you will get 1 here. So 1 into x power 8 is x power 8. Okay. So these two minus subtract operation, these two will cancel out. The remaining will be minus x power 4. Actually, minus 1 mod 2 is 1. So x power 4 plus x power 3 plus x plus 1. Okay, sorry. So this element x power 4 plus x power 3 plus x plus 1. So x power 8 mod x power 8 plus x power 4 plus x power 3 plus x plus 1 can be written as x power 4 plus, okay, I'll use x power 4 plus x power 3 plus x plus 1. Okay, so this modic polynomial can be reduced like this. Okay, so the modic polynomial which exceeds the degree 7 can be reduced like this. Okay, can you understand this first step clearly? X power 8 mod x power 8 plus x power 4 plus x power 3 plus x plus 1 is this, because x power 8 is not a group element of gf of 2 power 8. Okay, we have to reduce like this. Okay, now let's take this f of x. F of x, I need to perform x into f of x. Okay, what is x? X power 1. Okay, x power 1 term. So the x power 1 term is 1. Its binary equivalent is 0, 0, 0, 0, 1, 0. Okay, so this binary equivalent 0, 0, 0, 0, 0, 0, 1, 0. That is multiplication by 2. Okay, so we're going to find out, we're going to understand the simplified version of multiplication by 2. Okay, x into f of x. Okay, so how to do this? Let's take this equation b7 into x power 7, b6 into x power 6, b5 into x power 5, the whole thing. Okay, this whole polynomial to be multiplied with x. Okay, if you multiply with this x, you will get the polynomial like this. Okay, so this will be, if you multiply with x, definitely you won't get x power 0 term. Okay, so this will be x power 1 term. Okay, you won't get x power 0 term. You will get x power 1 term. X power 1 term. Okay, so this is multiplied with x. So this becomes x power 1 term. Okay, so b0 becomes x power 1 term. Okay, then you will get x power 2 terms. Okay, x power 1 term, x power 2, x power 3, x power 4, x power 5, x power 6, Okay, I need some more space. X power 1 term, x power 2, x power 3, x power 4, x power 5 term, and then x power 6, coefficient of x power 7. Actually, this x power 7 multiplied with x, okay, you will get x power 8 term also, okay, x power 8 based on the coefficient, okay. So what will be the coefficient of x power 0? So b0 into x power 0, x power 0 is multiplied with x, so this will be the coefficient of x power 1 term, okay. So this will be a coefficient of x power 1 term, b0 will be the coefficient of x power 1 term, and this will be b1, and this is b2, and this will be b3, and this is b4, and this will be b5, and b6, and b7. Okay, so just observe this. This will be the product of x into f of x. Okay, individually x is over g of 2 power 8, no problem. F of x is also over g of 2 power 8, no problem. But after multiplication, this may be over g of 2 power 8, may not be over g of 2 power 8. Okay, so that is based on this term alone. Okay, if this term, x power 8 term, if this coefficient b7 is 0, then this entire polynomial already over g of 2 power 8. Okay, no need to do the model reduction. But if the b7 bit is 1, then definitely you will have the term for x power 8, you have to do model reduction. Okay, so can you understand this point clearly? If the b7 bit, the most significant bit, okay, the most significant bit decides the operation. Okay, if the more after in the most significant bit, if the b7 bit is 0, this entire polynomial after reduction, the resultant polynomial is over g of 2 power 8, no problem at all. But if the b7 bit is not equal to 1, if the most significant bit is not equal to 1, sorry, not equal to 0, if it is equal to 1, then further processing is required. Okay, so the b7 bit decides the operation. Okay, so let's go ahead with this. If this bit is 0, x into f of x is nothing but b6 into x power 7, b5 into x power 6, b4 into x power 5, b3 into x power 4, b2 into x power 3, b1 into x power 2, b0 into x power 1, and 0 into x power 0. Actually, what is this? What is this? If this is represented as binary, then x into f of x, what about this? If b7 beta 0, what about this? What is this actually? Can you understand what my question? Let's take this. This f of x is represented as binary like this: 0, 1, 0, 0, 1, 0, 1, 0. Okay, this is b7 coefficient, and this is b6 coefficient. Okay, and b5 coefficient, and so on. This is b0 coefficient. Okay, x into f of x after multiplication, this will be the result. Okay, so if you multiply it, it's simply a shifting. Okay, now x into f of x is nothing but a shift operation. So 1, 0, 0, 1, 0, 1, 0, 0. Okay, so this is actually a simple shifting if the b7 bit is 0. Okay, if b7 bit is 0, multiplication by x is a single shifting. Okay, one single shifting. Okay, because the b6 x power 8 coefficient becomes x power 7 coefficient. That's it. Okay, x power 6 coefficient is b6. After multiplication by 6, sorry, multiplication by x, this becomes x power 7 coefficient. Only one shift. Okay, and x power 5 coefficient becomes x power 6 coefficient. X power 4 coefficient becomes x power 5 coefficient. Clear? So x into f of x is simply a shift operation if the most significant bit is 0. Okay, if the most significant bit is not equal to 0, then we need to do a different thing. Okay, please let me continue this on Monday. Okay, because it requires the adoption of this monic standard. Okay, so we have to adopt this, and we also exploit a modular arithmetic property. Okay, modular arithmetic property, we have to adopt this modular arithmetic property. That means a mod n into B mod n, the whole mod n is equal to A into B mod n. Okay, we have to exploit two properties. One is this modular arithmetic property, another one this monic polynomial reduction. Okay, so then only we can simplify this. I'll continue this on Monday. Okay, I'll continue this on Monday. Then we continue with the mixed column operation. Okay, because it may take 10 more minutes to complete. Let me complete this on Monday. Okay, so what we discussed today is simplification operation for mixed column round. Okay, mixed column round is based on multiplication of the polynomial ring. So we did a simplification for multiplication of polynomial ring as a matrix multiplication. It also requires multiplication of two polynomial over g of 2 for 8. So that simplification we are learning. So we complete this, we conclude this on Monday. Okay, any doubts so far? Or otherwise, if you can compensate on 10 more minutes, I can complete it. Can you tolerate 10 more minutes? Okay, nope. Because I think it's I'm stopping more so that I will continue this task on Monday. Okay, but before getting into Monday's class, go through this video at least once. Okay, go through this video at least once. Then only you can